Hey guys, it's Greg. Welcome to the first video on this channel in PyTorch. So we're going to load up the California housing dataset, put it in the format that PyTorch prefers. We'll make a neural network in PyTorch, and then we'll do the classic training loop to solve a regression problem. So let's get started. We'll start with import pandas as PD, just to grab the dataset. And I'll just copy this in because it's just for loading a dataset. We'll get two data frames, train.df and test.df. That is stored when you're in Colab in sample data and California housing train and test respectively. To look at the first few rows of the train, we see that each of these rows is an area in California with its longitude, latitude, the median of all the houses in that area, the total number of rooms in that area, a bunch of other variables about that area, and the thing that we're trying to predict is the median house value in that area. We'll set up a supervised learning problem, train a neural network, which takes in all of this stuff as a matrix up until median income, and then it's going to regress and try and predict the target column median house value. Now we get to the torch specific stuff, and so we will import torch, that's PyTorch, and then from torch.utils.data, we will grab tensor dataset. We're going to make a dataset out of these tensors, which is really the NumPy array. Because first, we're going to convert these data frames into NumPy arrays, and then we'll make it one of these tensor dataset things. So before we make it a tensor dataset, I'm just going to do some NumPy stuff to prepare it. We'll get xtrain NumPy, which is a matrix of all of our inputs for the training matrix. Xtrain NumPy is equal to train.df dot to NumPy. Then we want all of the rows, but we only want all of the columns, not including the last one. So this says xtrain NumPy is going to be all of this stuff, except then not the target variable. It's just our inputs. And then equivalently, we'll have something very similar. We'll have ytrain NumPy, which is going to be just our outputs or our target variable. And so the only difference is just the final column. And then we should see xtrain NumPy.shape and ytrain NumPy.shape. This should be, we have 17,000 rows and 8 columns for input, and then just 17,000 labels. We'll do exactly the same thing for test, and so I'll just copy and paste this in here, but convert this to test. So test, 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 same exact thing, except 3,000 rows for the test. So now we can load this up into the tensor dataset. So we'll get train dataset is equal to a tensor dataset, where we pass it the torch.tensor of xtrain NumPy and specify that the data type is of torch.float. And that's the x part. The y part is the torch.tensor of ytrain NumPy.reshape into -1 by 1, and again specify that it's a d type equal to torch.float, and then we should see that train dataset doesn't really look like anything interesting like that, but you can see it processed it correctly, torch.utils.data.dataset.tensor dataset. Now this is a tensor dataset, but what we actually want to do is wrap it in this data loader so that we can get automatic batching, and it's just a lot easier to actually do the training loop. So what we'll do is from torch.utils.data, we'll import this data loader. Then we'll get a train data loader equal to the data loader, where we just pass it the train data set and then the batch size, which you can set equal to what's good for your computer, whatever you're working on. 128 is fine. Since these are not images or anything really crazy taking up a lot of space, you can have a pretty big batch size. Now just to show you this works, if we do for x and y in the train data loader, then you can print the x.shape and y.shape, and we'll actually just break because we don't want to go through any more. And you can see here we have 128 by 8 and then 128 by 1. So if we loop through the train data loader, well, what it should have is an x matrix and a y list of labels. So the x.shape is a batch of 128 and it has its 8 variables, and we have y.shape, which should be 128 batch, and it's just one value. So that's it for the train data loader. Now we have to do it for test. So we have to go back and convert the test dataset into this tensor dataset. So I'm just going to go in here and then put the word test. In fact, I'm just going to copy from my notes because it's a lot faster that way. Same exact thing, except the word test is there. And the same thing as above, we converted that to a data loader. So I'm just going to copy in again for converting it to a test loader. So test data loader is the data loader given the test data set and a batch size of whatever, 128. We'll just do a smaller one, 64. If we print that batch of 64 by 8 and 64 by 1. So that's how to load up the dataset. It's a little bit different depending on what your dataset is, but because it was stored in a pandas data frame, we just converted that to NumPy, made it a tensor dataset, and then we pass it to the data loader. You'll pretty much always end up passing it to this data loader. Now we're going to make the model. So it'll be from torch, we'll import NN, which stands for neural network. And one big difference between PyTorch and TensorFlow is you specify whether things go on the GPU or the CPU. And that sounds really complicated because you start thinking about all the hardware stuff, but really it is as simple as you decide whether something goes on the GPU or on the CPU, and we'll see that. So we'll get device equals CUDA, which pretty much just means GPU, if the torch.CUDA is available, which pretty much just means you have a GPU. And if you don't have a GPU, okay, well then you better have a CPU, so otherwise it'll be CPU. And so we'll print that we're using the device, the variable goes in there, device, and if we run this, we should see that we're using a CPU device, because if you check the runtime on Colab, there's no hardware accelerator. Had we set that to GPU, then it would have said using CUDA. So now that we've done that, let's create a class, and you can call this whatever you want. I'll call it neural net, and most importantly, we're going to make it inherit from nn.module, and then we're going to create our init method. So define __ init self, and what we have to do is make sure to call the super method of the neural network. So we do super, and then neural net, the name of that class we made, and then self, and then we call its init, so dot __ init __, and then brackets like that. If you haven't seen Python inheritance, then this might look a little bit confusing. If you have, then this should look pretty natural. Don't worry about it, it's just something you have to do. Most importantly, in this init method, this is where you define or instantiate your layers. So you have to say what layers your model is going to have. Not necessarily what order they're going to be used, but it's at least going to say what layers it's going to have. Let's make a really simple model for now. We'll do self.hidden _ layer 1, which is equal to a neural network dot linear. And in PyTorch, the main difference between that and TensorFlow is you have to specify what the input is every time. So here, you pass the input dimension, which is 8, and the output dimension, well, this is arbitrary. We're making a fully connected layer, and so we'll choose, say, 64. And we also don't pass the activation here. We will say the self.hidden activation is equal to a nn.relu layer with those capitals like that. Note that I haven't specified that these two things happen in sequence. I've simply defined that this hidden layer exists and this activation exists as well. To finish off our model, we'll do self.out is equal to an nn.linear. Well, we have to transform 64. Remember I said it takes in the input, so the output before was 64, so now it's going to be 64 as the input, and to make this match our data, this has to end in just one thing. Again, see that so far I have not defined any sort of order. It's not like this is happening, then this is happening, and this is happening. That is what we'll make happen, but so far the way I've written it, it hasn't said at all what the order is. That is what the forward method is for. So we'll go down here and say define forward with self and x, where x is our batch of inputs. What do we want to do to this batch of inputs? Well, we want to pass it through this hidden layer, and so we'll say that x, the resulting output, is equal to the self.hidden layer 1 of x. We pass x through this hidden layer and it gets a resultant output. So after this happens, x is going to be 64 values, all ranging from -infinity to infinity. We will apply the ReLU function, and we've specified it up here, so we'll just do x is equal to self.hidden activation of x. Now we've applied the ReLU. We need to specify the output, so we'll do x is equal to self.out of x. Then we can simply just say return x. Since this is a class, we need to instantiate this class, and so we'll get a variable model is equal to neural net, that's what we called it, and it doesn't take any parameters because in our init method, we didn't specify it needs to. You could specify some in here, but it's just self, so it's just bracket bracket, and then we do dot to device, because you need to make sure that your model is on your device of interest. If device was GPU, it would send it to the GPU, and if it was CPU, well then it'll stay on the CPU. Now let's just print our model, and it prints in a very much different way than TensorFlow. As we saw before, still on the CPU, and this model is the neural net of it first has hidden layer 1. Note that that name shows up as your self dot whatever you called it. That's kind of cool. Hidden layer 1 is a linear of in features, it takes in 8. Out features, it makes it 64, and it includes the bias term as well. Then we apply a hidden activation, which is ReLU, and then out, our output, is the linear of in features is 64, and out features has to be 1. Again, note that these names are not necessary. If this was 3 T's and we had 3 T's here, then that is going to work just fine. I'm just going to go back to the other one though. So now we have our model. Next thing we have to do is set up our loss function. So what is it that we're trying to minimize? Well, that depends on the problem, but in this case, we're doing a regression because our output variable is these floating point values, and we're trying to predict one close to that, so that's a regression problem. Since it's regression, we'll set the loss function equal to, in this case, it's the nn.mse loss, so that's the mean squared error in PyTorch, and we'll set our optimizer. How are we trying to optimize this? This is equal to the torch.optim.atom, so that's the atom optimizer. You could use something else, and how it differs from TensorFlow is here we pass in the model dot parameters bracket bracket, and we'll also set the learning rate, which we'll set as 0.01 to start. So what this implicitly implies is this optimizer is only tied to these particular parameters. We're using this atom optimizer to only touch these parameters. We don't want to touch anything else, and we'll tell it how to adjust it in a moment. This part will look the most different from TensorFlow, because you're not just going to do model.fit and pass it the optimizer and loss function, you're actually going to make the training loop yourself. But it's really nice that way, and we'll see why. We're going to make a function called train. It's going to take a data loader, which has all the data, at least the training set. It'll have the model you want to optimize. It'll have the loss function you're specifically trying to minimize, and the optimizer, which is tied to this model's parameters already. Now what we're going to do is first set the model into training mode. In PyTorch, you have to do this like this. It looks like it means train the model, but actually it just means set it to training mode. And by default, we're going to set this variable train loss equal to 0, and we'll accumulate it. We're going to enumerate through the data loader with for I and X and Y in the enumerate the data loader. If you haven't seen an enumerate before, it just means grab the index and what was ever in it. We already looped through the data loader before, and so this is the batch of just the input matrix, and this is the batch of the labels. We're going to make sure these things go to the GPU, so we'll do x and y is equal to x.to device and y.to device. We need to make sure that our model and all of our tensors of interest are on the same machine. And then we'll grab our predictions, where we can just grab that with y hat is equal to model of x. We put our batch of inputs through the model that produces our vector of predictions. And from there, we can compute the loss on that batch. So that's MSE is equal to the loss function that we had, and it's going to be that given the predictions y hat and our actuals y. Then our training loss is going to accumulate. It's going to go up by the MSE.item. The reason we need item is just because this is a one-dimensional tensor, and so we grab the value of that tensor so that this is actually a number. Now the train loss is mostly just going to be useful to us. What's useful to PyTorch and for training the model is this MSE, which is the tensor that stored the computation of the loss function between the model's predictions and the actuals. That has a much bigger consequence than you might realize, because what it allows us to do is optimizer dot zero grad, that zeroes out the gradients, and then what we do is an MSE dot backward pass, and this MSE that is through that tensor, and we compute a backward pass through that, because that implicitly is a function of y hat, which implicitly is a function of the model's parameters. So really what it's saying is compute a backwards pass through this model's parameters. Anything that's trainable, we do a backwards pass through that to get the gradients of those trainable parameters. That's what deep learning is all about, because as we've done that backwards pass through the model, we have the gradient or derivatives of the parameters with respect to that loss function MSE, and that's what the optimizer needs to take a small gradient descent step in the right direction. So we can do optimizer.step. So we zero out the gradients, and then we do an MSE.backwards pass through that MSE tensor. Anything that's trainable, which is going to be through y hat, that's from the model. And so all of the model's parameters that are trainable, we do a backwards pass to get the derivative of those parameters with respect to that MSE, and then we take an optimizer step in the right direction. Since that optimizer already has the model's parameters, we're going to pass those in there. Outside the for loop, we'll get the number of batches is equal to just the length of the data loader, because however many batches we have, that's how many times we'll go through the data loader. And then we can get the train MSE value is just equal to the train loss, because we accumulated this through every batch. And then to get the overall MSE, we'll get the train loss divided by the number of batches. Technically, this value is actually the average training loss across batches, but it doesn't really matter. It's useful for us to report. And what we're going to output every time that we do a training loop, we'll do print f of the train root mean squared error, RMSE. That means the train MSE, but to the power of 1/2. That's just one way I'm doing the square root. There's probably a better way, but that's fine. We will output that. And if we run that, well, it's just going to make a function, but that's what we'll use for training. Now, as in TensorFlow, we keep switching between train and test. So here we're going to do test, which is going to take pretty much the same things. However, it doesn't need an optimizer because we're not doing any optimization during the training step. We will take a data loader, which will look the same. It's just going to be a test data loader. We'll take a model, and we'll take a loss function that we're not going to minimize here. We're just trying to report it. We'll set the model into evaluation mode. It just says, hey, we're going to be using prediction and not in training mode. And like before, we'll do test loss equal to 0 for now. Now, because we're not doing any optimization, we don't need to calculate any derivatives. So we can do with torch.noGrad, just means, hey, don't worry about gradients. And then we'll do the same thing. For x and y, we're skipping the index step because I didn't even use it anyway. For x and y in the data loader, we will get x and y equal to x.toDevice and y.toDevice. Make sure it's in the right spot. We'll still get our predictions. Y hat is equal to the model of x, and we'll do test loss is going to plus equal the loss function of y hat and y, and then that's a tensor, so we'll convert that to a value with .item. Now here we don't need to store the loss function into a variable because we're not doing any sort of backwards pass through it. We're just using it to compute the value of interest, and we're going to get the item, which just says get the number. Same thing as before after the end of the loop, and actually without the with part either because we don't need to be in there anymore. Num batches is going to be the length of the data loader, just how many batches we have. Test MSE is equal to the test loss divided by the number of batches. We're just averaging over the loss that was accumulated. And then we will do print the f of test RMSE is going to be the test MSE to the power of 1/2. And then there we go. We have a training loop and we have a test loop. Now, what TensorFlow is known for is model.fit, which is just something that keeps going between training the model and then testing the model. Here, we'll do the same thing. We have our test loop and we have our training loop, and so we'll keep just calling train and calling test in a loop for the number of epochs. Epochs means runs through the whole data set. So if we run through, say, 10 epochs, we'll do this 10 times. So we'll do for epoch in the range of the epochs, we will do print just which epoch we're on. I'm going to copy that just to save a little bit of time. So we're printing that we're on epoch plus 1 just because it starts at 0. And then we'll just do train. So train with our specific things. We had already got the train data loader above. We already made a model. We already had a loss function. And we already had an optimizer. And then test. It just takes the same thing, except it doesn't need an optimizer because it's not trying to optimize here. It's just trying to report. So we'll do test data loader, and model, and loss function. And here, it's going to keep doing these things, and it's going to report the numbers each time. Here you can see the train RMSE is going down, the test RMSE is going down as well, and that's really it. That's how to make a model in PyTorch. I'm not trying to show you how to make the best possible model for this particular problem. This is how you would make a neural network to try and solve this problem. I look forward to all the future videos on PyTorch. I really enjoyed creating this one. If you liked it, please drop a like and consider subscribing if you're not already, and I'll see you next time, guys. Bye-bye.